This is lecture 4, part 3. I'm going to turn current voltage curves into a practical application in chemistry, namely electroanalytical chemistry, in which you sweep the voltage applied to a cell containing an electroactive agent and then monitoring the current as a response. So I'm using a diagram that's familiar from the previous part, namely a pair of electrodes, an electrolyte solution between the electrodes containing electroactive ions, namely ones that can undergo oxidation reduction. They're going to be here represented by the cations. So a potential barrier exists at the electrode-electrolyte interface, which we described in part 2, and we can write this as a potential energy barrier similar to what you've seen in physical chemistry relating to particle in the box or whatever. The electron, here represented in blue, has a kinetic energy, a work function type energy, driven by the voltage applied to it, so the field parameters and so on. The square barrier there, looking like a dam, is the potential energy barrier at that interface, preventing the electron from being transferred into the solution, which would be to the left of the barrier. By raising the voltage or changing the voltage at the electrode surface, I can raise the energy of the electrons so that it is free to pass over the barrier and into solution, where it's waiting, where a cation is, or the cation is waiting, and one of the unoccupied energy levels in the cation can accept the electron. Initially, there's a uniform distribution of the electroactive species, here indicated by the red dot with the plus sign in it. And there's a zone. So a certain proximity is required for the electron transfer to occur. So if we have a certain region, the interfacial region, where the cations are sufficiently close to the electrode that they can be reduced, then once we've got the voltage high enough and the electron's work function sufficiently raised, as indicated in the cartoon diagram at the lower left, electron transfer will occur, and those cations will be reduced. The reduction of the cations will cause them to be reduced and eliminated from the zone next to the electrode. So what you do is you're essentially eliminating the presence of the specific species at the electrode surface, and they must be replaced by the species in the bulk of the solution. So diffusion process is set up. So once that interfacial region is vacated, one has to wait for cations to diffuse into the zone itself and then be reduced again. Well, not again, but I mean also reduced. So there's this continuous process of diffusion and then reduction while the voltage is applied to the system. So the current ultimately is determined by the rate of diffusion from the bulk medium into the interfacial space near the electrode surface. The electron transfer is actually faster than the diffusion rate. Hence that slope that goes like more vertical. So let's look at this in a little bit more detail. I have an electrolyte solution containing an electroactive species, namely nickel-2, which can be reduced by electron transfer to nickel metal, which will deposit on the electrode. So we'll ask the boss how we're going to do this experiment. And the boss suggests let's apply a potential of plus 50 millivolts to the cell, so where I've indicated on the voltage diagram on the upper left. And with time, we're going to sweep the voltage, the potential, in the negative direction until we reach about minus 3 volts. And this will be the nature of the experiment. So the boss is always right. You do what the boss says. We'll set this up as a current voltage plot. So we begin with a stirred solution now. We're going to have a stirrer going, always mixing up the contents of the solution. We're at the plus 50 millivolts. Note that we're reversing the direction of the voltage axis, so that negative is going to the right. And what we're going to do is sweep the voltage to about ultimately -3. All right, so we've got a linear region here that's dependent on the ions, the conductivity of the solution. So this is the solution conductivity zone. We'll note, however, that, and if we got continued on to -3, we would continue along that path, linear path. So, but this is where things get different now. We find that in actuality, as we hit a certain voltage, the current voltage plot becomes discontinuous. Remember, we had this situation with the diodes. So some other kinetic event is happening. There's a different type of current flowing from a different process, a different mechanism is taking place. And this different mechanism, in fact, is the electron transfer between the electrode and the nickel ions in solution. If we were to continue stirring the solution, we would find that this second discontinuity would likewise go up linearly and behave according, with the same slope until we hit -3. And if we reverse the direction, it would follow the same path. So we would have two linear sections. The second linear section, as I mentioned, corresponds to the kinetics, the current resulting from the electrode reaction, electron transfer from the metal to the nickel in the solution, thus reducing it. We would see on the surface of the electrode the deposition of nickel metal. So again, the nickel metal is deposited onto the electrode, reduction reaction. If I reverse it, the nickel will also come off the metal, go back into solution. And regardless of direction, as long as the solution is stirred, we would see the current go up and down following the same path. If we now change the concentration, we would wind up seeing that the discontinuity moves. It changes with potential. And if we change the concentration by factors of 10, namely 50 millivolts, 5 millivolts, 0.5 millivolts, we would see that the transition voltage shifts by 30 millivolts with each factor of 10. If you remember from the Nernst equation, the factors of 10 in the log give you the 0.059 volts divided by n. Since 2 electrons are being transferred, you expect 30 millivolts shifts with each decade of 10 in the Nernst equation. Okay, so specifically this parameter. So as the nickel concentration changes by a factor of 10, you add to the potential 30 millivolts. Okay. Now, when the solution is not stirred, there's a difference. There's a difference behavior. So you see the same discontinuity, but it reaches a limiting value indicated by the plateau on the right. So instead of continuing up in that linear fashion, it forms a plateau, and the plateau is roughly parallel to the original conductivity of the ions in solution before the electron transfer took place. This is known as the diffusion limited current. So this means that when the solution is not stirred, you have essentially removed all of the reducible species at the surface of the electrode, and the current is now limited by the diffusion of that same electroactive species from the bulk of the solution. So we call this I sub D, and it's proportional to the concentration in the bulk solution. We'll find out what the proportionality constants are in a bit, but this is the key point. The diffusion current at jump is proportional to the concentration of the unknown material in the solution. So also notice, and this is important when you solve problems or take tests, that you measure the diffusion current from the baseline indicated by that dotted line below. So in other words, the conductivity current voltage part. So that linear section that corresponds to the standard conductivity of the electrolyte solution. This is polarography. It's also known as linear sweep voltammetry, but polarography is an older term. People like to invent new terms, so you'll see in Harris, I think, as well, linear sweep voltammetry. Okay, so we'll go back to looking at the parameters in this polarigram or linear sweep voltammogram. You can derive the relationship. So physical chemists like to derive things. And I can say this because I happen to be one. But you can look at all the hydrodynamic parameters of a solution, namely treat the ions as rigid spheres, have a size, a shape, etc. And you can work out hydrodynamic parameters that relates the diffusion current to these hydrodynamic parameters and the geometries of the electrode and so on. For the most part, you don't really care about this. We can just calibrate the system using standard solutions and not worry about the derivations. In fact, the errors for analytical purposes are probably less if you just do standard solutions and compare the same way you do in absorption spectroscopy. So that's the tactic we're going to take. But I do want you to understand where these parameters come from. So there's something called the flux, namely the proportionality constant and the geometries. And so you just need to know that they do exist, that if you change the electrode size, for example, or the viscosity of the solution, you're going to get a different diffusion current. So we're sweeping, again, experimentally, we're sweeping the voltage in a sawtooth-like pattern, as we discussed at the beginning of this lecture part, and the resultant is the IV curve. So again, as I stated, the theoretical division, you have this as one possibility. I'll draw your attention to the denominator here, and that is the diffusion layer thickness. So this is why when you stir versus not stirring, the current will continue up in that linear fashion. So think about this in terms of that thickness. If that thickness goes to 0, which is the case when you stir the solution more violently, you decrease the unstirred layer at the electrode surface so that the resultant diffusion current is actually going to increase, and you're going to get that linear off to infinity type thing. So that's why there's a difference between stirred versus non-stirred electrochemical experiments. This thing we're just going to treat as a constant. We're not going to really care about this. There are various derivations. There's something called the Ilkovich equation, which is a very detailed representation of all the parameters that affect the diffusion current. I leave you to look that up in the textbook. It's not really important for our purposes. Know that it exists, but you don't need to derive it. It's primarily, an exercise taken by physical chemists. I will refer, however, to the A and the D there. The A corresponds to the area of the electrode. The D is the diffusion current of the ion through the solution. We'll just need that in one little derivation at the end of this part. Okay, so we've accepted this fact that the diffusion current is proportional to the bulk concentration. We're going to now look at the significance of this halfway point, namely what's called the 1/2 ID, and the voltage where that occurs. So our motivation here is to get some information out of the polarogram or the voltammogram. We know that the diffusion current gives us the concentration, namely tells us how much stuff is in the solution. But we notice that the point at which that discontinuity occurs is specific to the species that's in the solution. So copper would have that transition at a different point than nickel, than lead, than other ions in the solution. So we have a sense, therefore, that the position I've just indicated, the voltage that is at halfway up the diffusion limited curve, can be used as like spectroscopy. It can be used as a means to identify the material in the solution. And that's what we're going to demonstrate now in a little derivation. So we're going to look at the electrode reactions, namely the full reduction of the metal, the metal ion to the metal, but also recognize that in general, we can write it as a redox reaction where you have two ions. I'm going to call C subscript OX as the oxidized form of the species in solution, the one that picks up the electrons, and then that same species having gained the electrons, we're going to call that concentration C subscript RED. It's just for purposes of tagging things when we do the derivation. Okay, so the Nernst expression in this case is therefore going to be as follows. Note the sign convention. I'm going to play around with it a little bit, but this is the simplest form of the Nernst expression. Derivation, for those of you who need to be reminded, we did this in quantitative analysis. For those who did not take quantitative analysis, you can probably find the derivation somewhere in an analytical chemistry book. So I'm going to start initially with everything in the oxidized form. The solution contains an oxidizable or an electroactive ionic species. The current in our simplified form is some constant multiplied by the diffusion current, or the diffusion constant, and then the concentration. I'm going to specify and make sure that everything is in the oxidized form for the purposes of my description of the electrode reaction, and I'm going to specify, put in my subscripts as indicated. So this is for the reduction reaction at the electrode. I want to distinguish between the bulk concentration of the electroactive species and the concentration of that same electroactive species at the electrode interface. Cartoon-wise, I draw the electrode surface with this type of artificial map, so to speak. So there's a layer closest to the electrode, and everything in that layer can be reduced because of its proximity to the electrode surface once the voltage at the electrode surface is sufficiently high to promote the electrons in the electrode to pass the barrier and land on, so to speak, the electroactive species in solution. If the concentrations in these, and there's an artificial boundary indicated by that red dotted line between the bulk solution and the interface solution. If the concentrations on both sides of that boundary are the same, there's going to be no net flux of material from one region to the other. On the other hand, if I start to reduce the concentration of the electroactive species near the electrode surface, I'm going to start seeing a net flux of that same species from the bulk into the interfacial region. So, and if I, in other words, and also if I had a concentration that was higher at the electrode surface, I would see the flux go the other way. So that's the nature of the rationale for deriving or making the following statement about the current. So the current is going to be determined by the diffusion across that boundary. I've indicated now by the double arrows, and I'm going to represent that direction and the flux with that equation that just popped up. Namely, the difference between the concentrations in bulk and interface are going to give me the magnitude of the current governed by the diffusion, and the direction is going to be governed by the relative concentration of a concentration in the bulk versus the interface. So if you can see this, if, for example, if the concentration of the oxidized element at the interface is greater, the current is going to go backwards. It's going to go back out into the bulk. So everything kind of makes sense in terms of direction and is consistent with what we know about the current in the electrical sense, the current going from high to low. So that's going to go to zero once I hit the diffusion current. Namely, once I've reduced everything in that zone, that term is going to go to zero, giving me the diffusion limited current as the constants multiplied by the bulk concentration. And this is the thing that we talked about rationally anyway in the previous slides. So this is the same statement. Okay. If I rearrange the equation and these two equations and solve for the concentration at the interface, which is what's going to be used to get in my Nernst equation, I get the following. So I've substituted and kind of pushed around the top equation using the relationship at the bottom. And similarly, if I determine or I want to get the reduced form of the material, I realize that's going to be dependent upon the current. So in other words, the transition of the stuff in the oxidized form to the reduced, and I get the equation at the bottom. So these two equations at the bottom that I'm now flashing and pulsing excitedly, they're going to be what I just replace or substitute into the Nernst equation to follow. So I do that now. I return to the Nernst equation. I substitute the two concentrations from the previous slide into the Nernst equation. I get the following. So I get one log term expressed in terms of the current, and I have the second expressed in terms of the diffusion coefficients. When I look at the specific case of where the current is halfway up that ramp, namely 1/2 the diffusion current, and substitute this into the Nernst expression, that first term is going to disappear and go away, leaving me with just the Nernst expression in terms of the diffusion currents, or coefficients. The diffusion coefficients should not really be significantly different for the reduced versus the oxidized form of the species. So this term should likewise go away, leaving me with the relationship, namely that the so-called half-wave potential, the voltage indicated by the current voltage curve halfway up towards the diffusion limited current, tells you corresponds to the standard state potential of the electroactive species in solution. So the upshot is I have a polarogram, a current voltage curve, that has two pieces of information. The first is the identity of the material given to me by looking at the half-wave potential E1/2, comparing that to the standard tables of redox potentials for metals in solution, and using that to identify the material in the solution. Secondly, I can use the magnitude of the diffusion current as indicated to tell me the concentration of the material, that particular electroactive species, in solution. So polarography, voltammetry, is essentially like an electrochemical spectroscopy. I can identify the material from the energy relationship, namely the voltage, and how much from the response. So current here is analogous to absorption, whereas the E1/2 is analogous to the wavelength in spectroscopy. In referencing any of the textbooks that you've purchased, what I've recommended for the course has a specific chapter on voltammetry. The older books will have a chapter on polarography and voltammetry. But I will also point out to you, for those of you who've kept your textbook from quantitative analysis, that Harris has a very good chapter on the subject. The chapter title is called Electroanalytical Techniques, and there's a section specifically devoted to voltammetry. For references on the electrodes and the Nernst equation in particular, the previous chapters in Harris have all that material.